Good evening, everybody. My name's Alex, and Ron has invited me to come on in and tell you about using filters with visual astronomy, mostly visual. There's a little bit of astroimaging in here. And so that's what we're going to do. We're going to talk about through rose-colored glasses. Now, normally we've got two monitors here, and I get to read the script of what I'm supposed to be saying while you're watching the pictures up there. And it's on two different screens. Well, we don't have two different screens tonight, so it might be a little discombobulated because I've got to read the scripts over here while you're watching over there. But at any rate, those who see the world through rose-colored glasses tend to see things as rosy and perfect and pleasant. They go through life expecting the best, and they usually do get the best because that's their attitude. Now, us grouchy old pessimists say that these optimists may be fools, but that's a discussion for some cloudy, windy night when we can't be observing or something. I'm just using that old expression, he sees the world through rose-colored glasses, as a reason to launch us off into a discovery of how what you see when you look at something, when you look at the heavens, depends on what you're looking through. In particular, our perception can be changed through filters, changing the glasses to rose or red or other colors. And so what we're going to be talking about is a little bit of the science behind the use of filters for mostly visual observing. This all started a while back when a few of us were just starting out in narrowband imaging. One of our Riverside Astronomical Society members sent me a very nice picture of the, he said, looking desperately for the right button. He said, I didn't practice this on a different computer. How about that one?
Yes.
Yeah, that's what I believe too. That's why I pushed that one 4 times. It didn't seem to move forward though. Let's try a click. Here we go. Remember when I said this picture? Well, that's what I meant by this picture. Now I got to do the same thing over here. Hey, I'm confused. I think we all know the Orion Nebula. This is a picture from Alison Wong. I want you to note the nebulosity. Oh, that's going to be hard. And I want you to know, do we have a laser pointer? Never mind. Notice the nebulosity up there. The glowing colors. See how all the glowing colors, the red up here, up towards the top, is different from the red down a little bit below. See all the colors. Even the tannish brown around the trapezium is just a little bit different than that red. Notice the gradations of the brightness. I want you to notice in particular the Running Man Nebula. The Running Man Nebula is this little character down at the bottom going, oh, I'm running. That guy right down there in purplish. He's in a blue area, but he's also got a lot of red in it, so he's purplish. And well, if you were in fact looking through a telescope, you would not see that color because our eyes aren't as sensitive to colors as cameras. So here is the same picture as you just saw, only with the colors removed. And here is the narrowband image that was sent to us by Sam. And it was one of our first narrowband images. It was impressive to us. Of course, it was taken with a monochrome camera, so it could only show black and white. And it shows us the intensity or luminosity only, not the color. More importantly for our discussion, it uses narrowband and shows the luminosity of only one color of light. That color is very distinct red from the hydrogen alpha glow. And what disappointed Sam was that his Running Man right in here and completely run away. He wasn't there. He couldn't find his Running Man, and he was upset at that. And he was wondering why he didn't get a picture of it. That's not a laser pointer. That's a pen. I'm sorry, I'm discombobulated. I thought I'd be running this off a different computer. Capabilities. Yeah. There we go. Yeah, the running man is gone. And he was wondering why. Let's see, right. Here's Sam's picture. Here's my picture. I'm going to take a little bit of the color out of mine. He said, yep. This is the same picture as that one, except that the color's gone and it's bigger, obviously. Notice I am just taking the color out. The relative brightnesses are all staying the same. This brighter blue up here is still brighter down here. This bright blue is still bright down here. Everything has the same brightness it used to have. It's just that you no longer see the brightness of what colors that brightness had. Sam was complaining that his picture, wherever his is, did not show the running man very well. Boink. And that's the running man. Okay, now I'm now here. Anyway, it did not take Sam long to realize you're not supposed to be there yet. You're supposed to be back here. It did not take Sam long to realize that some of the running man area was there. Okay, in his picture, you can see some of the running man area. It's the blue area that you can see, but the red area is just not, oh no, you can see the red area of Sam's picture, but the blue area doesn't have the contrast anymore. And that's what the problem was. He had been taking the picture only in that narrow band red. He lost the outline of the running man. Before we figure out why all that happened, we're going to have to go back to high school a little bit. We're going to go to physics class, and then the bio lab, and then the chemistry class. And for those of you who didn't take it in high school, you probably took it in college. And I went to Claremont Men's College, which is right down the street here. Yay for me. Anyway, boink, boink. Usually that's just one boink and it all goes. Our modern understanding of light and color begins. Oh, yeah, those are the classes we were going. See, it's difficult. Our modern understanding of light and color begins with, there he goes, Isaac Newton, and a series of experiments that he did back in 1672 or so. Everybody knew back then that a prism of glass, when exposed to light from the sun, would generate a wide range of colors. He was one of the first people to understand the rainbow. He refracted white light with the prism and, of course, got that design, but he resolved it into its component colors, red, orange, yellow, orange, and this stuff had been done before, so it wasn't new. But he started experimenting, and at the time, everybody thought that when you broke it into a prism, it was because light was composed of two things, light, the red thing, and dark. And the more dark you had, the bluer it was, and the more light you had, and the less dark you had, I should say, the more red it was. But Newton put another prism in the line here after distributing it out like that, and he brought all those things back together, and he showed that, no, as a matter of fact, it is inherent in the light itself. White light breaks into all these colors and then can be combined back into white light. And of course, where are we? Yep. And of course, things are never as simple as when they were first discovered. 2 centuries ago, Fraunhofer had realized that the spectrum of the sun was a lot more complicated than the simple bunch of light that you see here. Where is that? There, okay. remember looking at the illustration, we only had this band of light from one to the other. But with Fraunhofer, we actually had lines in it. And he wanted to know what those lines were about. So he did some checking on all that. And he eventually told us some things, and we found out that light comes in a broad range of what are called wavelengths now. And if they're very small wavelengths, about the size of a bacteria, well, they're called gamma rays. And if they're very long, about the size of a building, they're called the radio waves up there. And it's only this little band right here in the middle coming out of the sun. There's actually a lot more coming out of the sun, but that's the only part we can see, the visible light. All right. And yeah, knowing that there are lots of kinds of lights, we've developed many kinds of sensors and many devices to use these different kinds of lights. Now, this is all good to know, and we're going to return to it later when we get to chemistry class. But really, our discussion must return to, well, it's hard to see from here, the visible range of light right in there. That's all we really need to know about. We don't need to know about everything down here and everything up here, but we're going to talk about it a little bit. In order to understand why we need to talk about the visible range of light, we need to go over to biology class, which is right around the corner here. There we learned that the eye has a retina with two kinds of sensors, rods and cones. The cones see color, but the rods don't. Cones come in three colors. We like to call them red, green, and blue, but in fact, they're more blue, green, and yellow that stretches off into the red. Okay, but we call them red, green, and blue. The green light is not very sensitive down low, gets very sensitive in the green range, and then it's not very sensitive up here. Okay, so that's why it's called the green cones. Where are we going? And the different cones, of course, see their different colors. So actually, we have what are called red, green, and blue sensors at the bottom of our foreheads. But the analogy to the RGB works pretty good if we understand how an RGB color monitor works. As we saw from Newton in physics, that mixing of all those colors, of all those three rods, gives us all the colors in between. In fact, if we mix all the colors of the right proportions, we get what we call white. If we see relatively more red than we see green or blue, then we'll get a reddish cast to everything. Hang on, it's not moving like it should. What if we were to knock out one or two of those cones, one of those two sets of cones, red or blue or green? We all know that some people are colorblind. That means that some of their cone receptors are not working very well. This is a standard chart for eye tests here, this one up here. All right. And as you can see, if you can see the number 57 on the screen up there, you're not colorblind, or at least not this kind of colorblind. But alas, if your blues and greens were not working, your blues and greens, you'd see something like this. Actually, you'd probably see something like that. But for our purposes, you can see if we take the blue and green out, you can't see the 57 anymore. That's if those particular cones are not working. Now, this is an important distinction. The eye brain is not good at seeing things all by themselves. In the absence of other clues, we cannot tell how bright something is. We can only tell how bright something is in relation to other things around it, including all of the, including the rods and the cones working together. Now, astronomers, of course, don't use our cones very much when we're at the telescope. That's because they don't work very well in dim light. Therefore, the other sensors, rods, take over. They're monochrome. Oh, they don't see in color. And they pretty much see this. They pretty much see shades of gray. So at night, we have no hope at all of seeing the 57. Luckily, there are 18 times as many rods as there are cones, so that we can see what we can see, we can see better. But rods don't see the color, just contrast, the difference between black, white, and all the shades in between. Yeah, I'm getting pretty good at this. No, I guess I'm not. I take it back. I'm not. And remember, earlier I said that if we mixed red, green, and blue in equal proportions, we would get white. Well, I lied. Our brain has much to do with telling us what color we are seeing as the actual light coming from the object. This is because of the sensing contrast as much as the absolute values of the light. It's not just how bright the light is or what color it is. It's how bright the other lights are and what color the other lights around it are. What I said about intensity and brightness holds for color. Our eye brain system does not see the absolute values. Check this out. What color is this square right here, and that square right there, and that square right there? Click. No, I wasn't supposed to click that. Yes, I was supposed to click that. That moves to a different slide. This is confusing to me. Okay, I can still talk about it. Let me see. Yeah, here it is. In fact, all three of those are exactly the same color. Okay, if you use Photoshop, you know that there's a tool you can use, and all three of them have a red value of 128, a green value of 71, and a brown and a blue value of 14. They're all the same color. And I don't know why you can't see that. Let me see. This is the one I was supposed to click. If I take away the other squares around them so that you can't contrast them, you can easily see that they're all the same color. But if I take it back, see, so I wasn't lying on that one. I don't know what this slide is doing here. Hi, slide. What are you doing here? Okay, let's go down to this one here. And yeah, so far we know we cannot see colors. We see contrast. And how do we use this in astronomy? Well, we've got to stop off in the chem lab for a minute or two to find out some more of this stuff. So let me see if I can figure out how to stop in the chem lab over here. Remember Fraunhofer and those mysterious lines in the spectrum? Well, what caused them? I'm getting good. Let's ask this well-liked fellow named Robert Bunsen. In the mid-1800s, Bunsen was asked to develop a new flame that could generate heat without generating a lot of smoke or light. That's why you could use it to heat things and then study the intrinsic color of the thing that was being heated rather than the light around it made by the lamp. Heat without light. In the summer of 1859, Bunsen began a systematic study trying to form what are called prismatic spectra of these colors. By October, he and Kirchhoff had invented an appropriate instrument that they called a spectroscope, and had actually found lines like the ones I showed you in the last picture in various chemical elements. They included, he said, getting lost in his reading. Was it lithium, iodine, and one other? I don't know, but we'll look it up later. Each chemical element that they tested contained a unique spectrum. It provided like a fingerprint, which can confirm the presence of the chemical. They realized that this could be used as a powerful determination for the chemical composition of the sun and the fixed stars. In other words, by finding out where the holes were in the spectrum or where it was particularly bright in the spectrum, one could figure out what chemicals were making up that far distant object. This is getting annoying. And you got to catch up too. Ah, there we go. Hydrogen, helium, carbon. See, they've all got particular lines in particular places that can tell you what things are. One could sit in one's lab and look at the spectrum of light being emitted from heated, glowing objects and see what elements were in the object and deduce what the temperatures were of that object. But one could look at also the light from a very distant celestial object and see these exact same lines. Here are the lines that you would see from helium, hydrogen, and carbon. They're the same whether you're looking at them in the sun or in your lab. Here's a kind of interesting set of pictures, and we're out of the visual range now. The main argument of this evening's presentation is that by using rose-colored glasses, specifically different colored filters, different designed of filters, one can change what one can see. This is an exaggerated version of that. Instead of just changing a color taken from the visible light spectrum, I'm jumping from one end of the electromagnetic spectrum all the way to the other end of the electromagnetic spectrum. In other words, all the way from radio, which are the very long wavelengths, down to high energy X-rays, which are exceedingly small wavelength objects. And you can see some structures remain no matter what. Other structures, no, that does not look like that. That does not look like that. See, some things are the same, some things are different, depending on what you're seeing coming out of it. And what you're seeing coming out of it depends on what you're looking through. Boink. So we're going to regroup. Yeah, that's right. We know that when working in color, the eye uses three sensors, a red, a blue, and a green, to see the colors in contrast. This may do us some good when we're looking at something bright enough to have color, like a planet, but it does not do us much good when we're dealing with dim, faint, fuzzy objects. We know that the eye-brain system sees contrast, not the absolute values of light. We know that the different elements glow in different colors. Even though we may not be able to see in colors, we find something that allows us to manipulate the intensity of different colors so that we can see between the various elements. That's when we need rose-colored glasses. Now, all that we've covered so far has been pretty much theory and the science behind how filters work. From here on, we're going to be looking at some of the filters and see how they work in particular. Specifically, we'll be talking about two major types of filters, the planetary and the deep space. Planetary filters are simple colored glass that absorb most of the light and let one major color pass through. Deep space are much more sophisticated pieces of glass with special reflective coatings on them that bounce light around in such a way that only very specific narrow bands of light get through. Let's see how all that works. This is, my friend, Mars. Why didn't you go where you belong? Oh, I know why. Blink, blink. There we go. Let's take an example of Mars. Mars is predominantly red because of the rust on its surface, but it has some blue areas. Red, blue, even got some polar caps, white. What if I put a filter in that would allow the red things to show through while cutting off the green things? Okay, that wasn't right. I got to do it over here. There we go. Like this. Remember? The red things can show through, but the others not so much. Now look at how much easier it is to see the 29. Okay. Well, let's see what happens. No, I don't have to do it here. I'm lost. Help me. See the number 29 up there? Now you see it? Well, it pops up 29. It's always been there. The 29 has always been up in here, but you couldn't see it until I got rid of the colors that didn't, until I got rid of all the colors but the red. And then the 29 popped through. Click and clickety. The same thing can be doing by putting a deep rose colored, red filter on Mars. These are the red areas. Okay. Notice how they stay white and bright. The blue areas, they don't come through nearly as well. All right. Since the red filter is not letting in any of the blue, we would expect the blue to be dimmer, and dimmer blues with just as bright reds means greater contrast and thus more visibility. Similarly, the blue filter would keep out the blue things. Okay, you can see the blue things better or as well, but the red filters don't, the red stuff doesn't come through as well. But with either filter, we see the polar caps better. Okay, that's because the other lights are being held out. And, oh yeah, that was supposed to go in there someplace. Anyway, in the previous slide, I manufactured those pictures with Photoshop, showing you what you might see with the red or green filter hiding things. In this actual monochrome photograph affects the same thing. For instance, here we've got big Jupiter, and you can see the great red spot up here. If you make so that only the red comes through, it doesn't show up so much. But if we cut off everything, you notice that the red is blacker here and you get more contrast. Okay. You see the red better with the green filter on it. You put different colored filters on it and you're going to get a different effect. If you put a red one over there, the red spot disappears kind of. Orange, it's starting to come through, and green. So you can see you can move things around like that. These filters are called planetary filters. Oops, that's not on the same one. This one's on Oink. These little buggers are called planetary filters. They come in many colors, but a basic set of 4 is, they'll do you for a long time unless you get really obsessive. The set from Orion cost $49.95 and includes number 15 deep yellow, number 25 red, number 58 green, and number 80A a medium blue. Those numbers, incidentally, are left over from black and white film days when all filters had a standard number to ensure that folks could get the repeatable exposures in their black and white imaging. They generally screw into a 1 1/4 eyepiece. And they're really quite handy, and everybody should have a set if they're looking at things. If they're looking at things on planets. Here is a planetary filter guide for you, and you can see that if this is what you want to see, you use this filter. If you're looking at doing this kind of stuff, you use that filter, and so forth and so on. These are available in various places. This chart. If you look up on the internet about planetary filters, that's what you'll find. Like I say, 4 of them will pretty much do you. You can go overboard, and many people do. I do it sometimes. Check out how many different filters, for instance, in this, they suggest that you use for the Maria on the moon or on Mars. How many different filters they suggest you use. Come on, man. You really need that many filters in life? I don't think so. But you get the idea. The different filters show you different things. Having said that 4 will do, I do want to cover some specialized filters that would do you some good when you're observing for specialized planetary filters. Some companies have some filters for observing Mars. They're not quite the same as the previous filters I have been talking about. They were just basically colored glass. These are a little fancier, made by depositing special coatings that reflect some of the light and let others pass by using optical interference, where the waves of light interfere with each other. I'll read you the description of the Orion version of it. This custom designed, says Orion, filter enhances contrast of virtually all surface features. Dielectric coatings transmit violet, blue, and orange red, which are what you're going to see mostly on Mars. It gives you this stuff, but it doesn't give you the stuff in the middle, which just confuses stuff. Polarized caps appear more sharply defined, and differences in landscape shading are nicely resolved. Polar hazes and cloud cover become visible. The filter's high transmission makes it effective even in small scopes. High transmission means that it's letting in almost all the light, except for the part that you don't want, and it's letting in none of that light, or very little of that light. TeleVue makes two Mars filters, one for enhancing surface detail and one that achieves penetrating high contrast surface views. I don't know what that means, and how they're different. I don't really know, but I know that they do make two of them and apparently make money off them. And go to the next slide over there, and the next slide over there. There's also such a thing as a neutral density filter. You've been seeing all those graphs where the red's on one side and the blue's on the other side. Well, a regular planetary filter will give you the red or the blue, depending on what color it is. But lunar density filters, neutral density filters, dim all the light. All of you have looked at the moon with a telescope, and it burns a hole in the back of your eye. That's not good. It's much more pleasant if you cut that light down to a quarter. And so you can use a neutral density filter to get more detail on everything. Now, neutral density filter has nothing to do with this picture of the International Space Station crossing in front of the moon. He says that I took the picture and I got to show it now and then, and I just thought it'd be cool to bring it up. So that's why you're seeing my International Space Station. See those guys hanging off the edge? They're going to make a decision about bringing them back in August, or maybe, never mind. There's some things you got to know about all filters, particularly planetary filters. They all cut down light. You're gonna have less light after you use them. They all create a color cast. You're dealing with bright objects on planets. If you use a green filter, everything will appear green, and that's not a natural color. So it's going to look a little weird. So just keep that in mind. But there's one other thing. Much of what I'm telling you right now is real. Okay, I'm not lying that much. These filters do increase the contrast and thus the visibility of the objects and the details of the objects. But much of this is what's called a Hawthorne effect. The Hawthorne effect, if you remember, as a matter of fact, I learned it here. Down the road here in my econ class. It was a study of industrial efficiency. They wanted to see what the effect of lighting was on a workplace. And so they said, let's increase the light by 10% and measure the output of the workers. And yeah, production went up because they were 10% more efficient or something. That's interesting. I wonder what happens if you do it again. Let's say they increase the light 10% more. And yep, it didn't go up quite as much, but it still went up. So let's try it again. And they did it again, and the efficiency went up. And they said, whoa, that's weird. What happens if they have less light? And so they decreased the light. Okay, now the experiment is we're going to decrease the light. And guess what? It went up again. All right. The fact is that the light wasn't changing anything. The fact that they were being experimented on is what was changing the efficiency. And so you can often fool yourself into thinking something has improved when in fact it's just different. If you don't believe that, remember back to your college days when audio systems were all the rage instead of all this computer junk. And all you got to do is change speakers, and those new speakers are much better than the old ones. And then you put your old speakers in after a while and they go, oh, those are much better than those other ones. And it's just the difference that makes the difference. The fact that you've changed things that makes you feel like they're better. Yeah, I probably messed up that time. Okay. But this filter stuff does get a little bit better than that. We've just learned about manipulating light, letting some in while others block. But it can be applied to deep space objects. Let's say you wanted to see something from the city. This is neither a planetary nor, strictly speaking, a deep space filter. But on a good night, this might be what you see with the Orion Nebula. There is some glow in the right places, but there's nothing like the cool things we saw a bit earlier. Notice also that the sky itself is not black. It's a hazy, low contrast gray. That's because of the light pollution as it bounces off dust, aerosols, and all the other things in the atmosphere. Without that light and air pollution, it would look something like that. And then he asks, the key to making that look like, oh, heck, I don't know where I am. That, it looked like that without without heading out to a dark sky site, or is to figure out what colors you want to come through the filter and what colors you don't want to come through the filter. As we know, the sun has all the colors in it. Okay. Well, this one's going to be weird to do because there's a whole lot of manipulation in this slide. And so you start with that, you figure out what's causing the problem. Now, we've known from high school that we've got a full spectrum, contains all the colors of the rainbow, red, blue, green, and all the kind of weird stuff in between. But remember, the work of Bunsen, Kirchhoff, and others, we know that not all light is continuous, but every element has a characteristic color. And for those of you who remember this stuff, you've got LP sodium light out there, and then they found out that HP sodium light was a little bit more. And then everybody went to mercury vapor. And remember that for a while, everybody had those orangey, glowy lights, remember? Well, what colors are those lights, really? Here. Well, it turns out that depending on which light you put out there, they're actually not continuous. They aren't all the way through. If you have some of these, almost all of them glow very brightly in this range. Okay, but none of them glow very brightly in red, and except for this deep blue that you see across here, none of them glow very much in that. So all you got to do is figure out what are the chemicals that they're putting into the lights along the street. That's what's causing the light pollution up there. So don't let them see those colors, but let them see all these colors and all those colors. Oh, that was weird. Hang on a minute. Okay, we're going to go here and here. These are the common light pollution emissions. Here. You saw them in the other graph just a minute ago. Is it possible to get a light filter that blocks out this range and blocks out that very small range, but lets in all the others? Yeah. It is possible. It's called a light pollution filter, an LPR, light pollution reduction filter. Yes, ma'am. I can't hear very well.
What do you mean by pollution there? Common light pollution emissions.
Yeah, so she goes, what do you mean by pollution? Light pollution. So it's light that's not naturally occurring in the sky. Okay, it's light that we produce that it's being bounced up in the atmosphere.
So it's hard.
You go give the rest of the show.
No, it's street lights.
Yeah.
Street lights.
What is light pollution?
And the city lights are making street lights in the bright sky. All kinds of things.
When you go out to the desert, it's nice and dark and you can see the Milky Way, right?
Right.
We don't. But when you go out to Victorville, which is just as much in the desert, you've got streetlights all around you. And it's bouncing everywhere, lighting up the sky. So you can't see the Milky Way very well. That's light pollution.
Yeah, but you're, okay, I understand light pollution,
Oh, I've lost my translator.
Go ahead.
but you have two blue. And then you've got that long area where it's a very nice blue.
This
light
is the
blue.
light from the street lamp. That's the light from the street lamp. In between, there's no light from street lamps. You think you're seeing a white light out there under the street lamp, right? You're not. You're getting some blue cones excited, some green cones, some yellow cones, and some red cones excited, but not all of them. I mean, yeah. The light from a street lamp is not continuously the full color white light of rainbow.
I
That's an
can
important thing to remember.
Yeah, I can understand that, but there are any kind of light will have a spectrum of some kind.
Yes, I don't remember which is which, but that might, this one, that one, and that one, the scientists made the element glow in those three colors. Those three colors are close enough to red, green, and blue that they make it look white.
So that's the light pollution for a typical set of city lights. Right?
Yeah.
I'm just showing you what it looks like if you actually could see all the different colors. That's what it would typically look like if you went different.
A low pressure sodium lamp has a little bit of blue, a lot of yellow, and a little bit of red. A high pressure sodium lamp has a lot of red, not so much of the yellow, some green, and it looks like a little bit of blue in there. Okay, but you'll notice it doesn't have any of whatever this is.
What about LED lights?
Did you look at the slide pack yet? No. Smart kids. Did I cover that? No, not convincingly. When you look at a street lamp.
Yeah.
Let's take the most extreme examples. You know that there are some street lamps like down at Ontario Airport. The UPS area glows in an orange. Okay, well, I would say it's probably using this kind of lamp because it's got the red and the yellows. But you can go to other places where you're getting pretty much a yellowish, get in there, but you're not getting the other colors so much, maybe a little blue. So you've seen different colored street lamps out there. What you don't realize is that they're not putting off a continuous spectrum, slightly shifted to one, but they're putting out lines of light. They're putting out lines at 400 and 600 and 550. They're not putting out a continuous stream of light from 400 to 600. Okay, and that's what people don't understand. And that's how these filters work. They find the places in between where those lights are not putting out light. And they let you see those, but they don't let you see this stuff. So the stuff that's made by the street lamps doesn't come through. You can't see them, it's blacked out. Only the stuff made by other light can come through. Okay, let's move on a little bit here. Okay. Orion and a number of other companies sell what are called light pollution filters, which do essentially that thing that we just talked about. Here's what Orion says their narrowband filter does. My display got screwed up here, so give me a second. It lets no light in here and no light in here, but just all the light that comes in right through there. And you'll notice that's where this emptiness is. Okay, so light that's coming down from above hits this filter and it stops. It can't get by there. So that line is blocked. Light coming through here is blocked. So And did I see? No. You see, it won't let light here, so it's blocked. That's how a light pollution reduction filter works. It helps the object stand out. And I think I got yeah. These light pollution filters come in different styles. Okay. This is, for instance, is the one we just looked at. See, it goes up there. This one's very high here. And I think there's another line out here that it picks up. But those are the lines. Remember, it's all got to block out. So you can see how it's trying to fit that curve. Fit the part where there's street lamp light, they don't let you see. The part where there isn't, they do let come through. What you're looking for is better contrast all the way through. Here is another graph of the same kind of thing. These along here are they're the same things you've been seeing as far as what color lights are coming through. This is like different elements coming from the sky. This is from street lamps, generally speaking. They also come from the sky, but they're more coming from street lamps. And so it lets a lot more light in right through here, this portion that you want, and then it lets a lot more back up in here. Okay. Blink. Why is that slide in there, Alex? You can see it again there pretty clearly. Now, this is the spectrum from the sun. This is the solar spectrum from the sun arranged in a different way. But you can see that this is 0 and then it gets higher and then it's pretty much smooth all the way along. This is a old-fashioned street lampish thing. This is LED lamps. And this was the question that was just asked that I shushed off because I didn't want to give the surprise. We're going to have a problem someday with light pollution rejection filters because remember, they're made to show you the parts that you want to see, but cut out the parts that you don't want to see that are made by, well, in the future, the lights, the LED lights, they do put out a full spectrum. They don't have those holes in the middle of them. Mm-hmm. And that's going to cause us a problem eventually because there won't be any holes to look through to make these light pollution filters work. And that is the answer to the question you were looking for earlier. Now, it's hard to believe perhaps that just changing a filter can change what you look at, but that's not what's supposed to be there, is it? Yeah, oh well. But looking at the rosette may help us see what we're talking about. Let me see, where's that slide? There's the rosette. Hang on a second. Okay. Here's the rosette. It's a broad spectrum, meaning we let in all the light, and so much of the light there is red that it comes out to be red rose. Taking a look at the next slide, this is that same picture, only we're taking just a very narrow slice. In this color, that's what you're going to see. In this color and this color, they're almost the same. You might think they're the same, but this is a hydrogen alpha and that's a sulfur 2. And you can see that they're actually different because the hydrogen sulfur, or hydrogen, the H2 is now hydrogen alpha is there's more hydrogen up there than anything else. And the sulfur looks a little different. So those are 3 different pictures taken with 3 different filters. And this is how typical narrowband imaging is done. And you can see that they do look different. See all this red in here? Not over here, not as much of it, and hardly any of it right in there. Okay, that's because there's different elements in there glowing at different temperatures all the way through. Oh, stop it. Usually if you're working on one computer, this is all a lot easier. Now what we're going to do for the next little bit, we were finished with the rosette. Oh no, we weren't finished with the rosette. Back up a little bit. So you get 3 different pictures of the rosette, and depending on how you combine the colors and which colors you assign to which, you can get completely different views of the object. Is that where I am? Yeah, we're together. Now, this presentation is about the use of visual, and that was narrow band. You can't really use too much of a narrow band. There are narrow band visual filters, and there are narrow band photographic filters. The photographic filters let in a very small slice of light compared to the visual, and you can very rarely actually see through them. Back to the visual. I don't know if you can read all that, but you can certainly get the idea. This chart is available in various places also, just like the other chart. For stars and stars clusters like M13 and M11, the best filter for viewing it is none. Those objects are full spectrum. They have everything in them, all the light, all the white light. Okay, so you don't want to filter on at all for those. All right. And if you've got diffuse nebula, the kind of gaseous nebula, well, an O3 is good, but they're very dark. The ultra high contrast is like one of those light pollution filters. So you can get various types of deep sky filters and use them in various capacities over here. Some are used over and over again. Okay, that's one of the things you can get out of deep sky filters. And let's start looking at some of those recommendations. He said, trying desperately to move ahead. Stars and clusters you don't use any because they are basically white light. These are the emission nebula. The characteristics these have in common are that they glow like a fluorescent light bulb. They're full of gas, largely hydrogen, but also other gases and dust. Their light output is not uniform across the visible spectrum, so you can benefit by emphasizing one part or just a narrow band of light. What the charts here call diffuse nebula are widespread areas extending over 100 light years or so. Diffuse nebulas are clouds of interstellar matter, namely thin but widespread agglomerations of gas and dust. If they're really large and massive enough, they are frequently places of star formation, and they generate big associations and clusters of stars. Some of the young stars are often very massive and so hot that they're high energy. They radiate and they excite the gas of the nebula, which is mostly hydrogen, to shine. Hydrogen shines in a red. Planetary nebulas down here develop differently, and so they've got a different collection of gases. This is the diffuse nebula up here. And so you use slightly different kinds of filter on them. Excuse me. Excuse me. There are such things as faint planetary nebula. These are very small objects, and usually an O3 filter will bring them out because there's a lot of oxygen in here that's been made to glow by usually the remnant star of what was behind it. that the planetary nebula came from. So O3 filters are pretty expensive and they're pretty dim. You have to have a very big telescope in order to use these things, gather a lot of light. Reflection nebula are like, this is the Pleiades, and you can see there's a lot of gas up in through here, they're made to glow by these stars here, lighting up all they're reflecting. The blue lights of these stars are reflecting in the dust all around the stars. And usually a deep sky filter would be good for that. That's the light pollution reduction filter we talked about earlier. The next type of sample they've got are the spiral galaxies. Right. No, they aren't. Spiral galaxies, we already decided we don't use none. The next one is the faint nebula. And again, O3 helps bring this out. This is the North America Nebula and the owl over here. And you need a veil, the rosette that we talked about earlier, the North America Nebula. This is North America right here, that's Florida. And deep sky filters, those are the kind of filters you'd want to use on this. And then the last kind of deep sky filter, I've got this right. Now, when things get really dark, there's simply not enough light to go around. And we are actually describing extremely faint emission nebula here. It's true that the Horsehead itself is not an emission nebula. That's the Horsey right there. Okay. And that's actually a dark nebula. And the filters don't bring it out. What the filters do, it brings out this stuff behind it so that that'll show up. Okay. It's dark, collecting dust and not emitting light. I don't own a H beta filter because they're pretty highly specialized and take even a lot more light. They're really dark suckers. Everything gets dark in the eyepiece because nearly everything in the spectrum is blocked, and there's not much H beta itself present. But those things like Ron, one of the really good visual observers, he knows that they can kind of bring stuff out with this H beta filter that he can't see otherwise. Okay. I just don't have enough experience with them to say that. Now, where are we? Here.
Hey, Alex, can I ask a question? This is Ron Ugolit.
What was that?
Is the question.
Can I ask a question?
What was the question?
I haven't asked it yet.
Can you speak up? It's coming off their speakers.
Is it from God?
Yeah. Run.
Oh, please repeat yourself, voice from beyond.
Okay. Actually, I'm a little confused in the previous slide when, for example, you were looking at the Rosette Nebula and you were suggesting that an O3 filter would enhance it, but it doesn't glow very much in O3. It glows in hydrogen. Wouldn't you rather use a hydrogen filter to let that light through and block out everything else?
Did you guys get that?
Would you rather use?
All I got was Ron's not that good an observer.
Yeah.
He was just asking if a hydrogen filter would be better than an O3 filter on the Rosette.
What was the question?
He was asking if a hydrogen filter would be better than an O3 filter for the Rosette nebula.
I don't have enough experience to tell you that.
He was stating that they didn't think there was much O3 emission from the Rosette. That there wasn't much O3 emission from the Rosette.
Right, but what it may do is hold everything else back, letting the Rosette light come through. Remember, that's what we do with some of these things now. Okay. I'm sorry, I don't really have the answer to your question there. Now, charts like those, like the ones we just worked our way through, can be a little bit confusing. The chart I just showed you from Lumicon, for instance, is not the same one as from Thousand Oaks or Teleview. There are differences of opinion. Their recommendations are different, even though the bandpass graphs, and you're seeing, you're seeing bandpass graphs here, but their recommendations are different, even though they've got the same graphs of which light should be showing through. With all this confusion, it might be worthwhile to try to summarize. There are differences, but generally speaking, we can call all of these deep sky filters nebula filters. To start with, recall that once upon a time, everything in the heavens was either small and sharply defined, a star or a planet, or was large and fuzzy. Ill-defined objects were cloudy, and they used the Latin word for that, nebula. Planets are bright enough and stars are generally complete spectrum, as are galaxies and star clusters, which are made up of stars. So the purpose of these deep sky filters are there to bring out the nebulosity in the fuzzy objects. By design, there are three major kinds in general use: broadband, narrowband, and line filters. Broadbands have generally wide areas that they cover. They block the critical light pollution bands we saw earlier, but as you can see, they let in a whole lot of light. They're useful for observing in light polluted areas. Narrow bands have relatively small areas where light can pass. Relatively small areas where light can pass. They're more for specialized study, looking for O3 or H beta areas, and some for hydrogen alpha, although hydrogen alpha is beyond what your eyeball can actually see. So I'll leave it at that. And here's a simplified view of line filters. And it kind of rates on the scale of, how good they'll be for you. You can't afford, actually, you probably can't. I don't know how much you guys make, but these things cost in the hundreds. Remember, we started off with little plastic or with little glass planetary filters. They would cost $5 at the swap meet. These 150 still at the swap meet. So be careful with them. And how did we get down there? How will we get back down there again? Oh, that's what I was saying. And remember to generalize. Remember, no filter will make anything brighter. You can only lose light. You will never generate it with the filter. See all these bandpass transmission numbers? See all of them? They all top out at 90 something or 80 something. None of them hit 100. Maybe there are some, but they know none of them pass all of the light that are going to be. Everything will be darker. If your scope is not big enough to gather the light in the first place, you may not get that much benefit from the filter. In addition, since you are emphasizing color, one color over another, nearly everything that does remain bright, mainly stars, will have a color cast to them. You'll have green stars or blue stars or something like that, depending on what color filter you're using. And even with the bandpass filters like these here, they will leave a color cast. Also remember that Hawthorne effect. Many times it's the change of what you are doing that matters, rather than the absolute view of what you've got. It's your brain making the difference because you can see things just a little differently. And so you think they're better or something. A good way to try out all these things is when you go to a star party where people are hanging around with all this stuff. You ask them, hey, can I, and you hold that thing up, and you don't have to put it in the telescope, but just hold it between the eyepiece and your eyeball, and it'll quite often show you what you want to see. Okay. Watch out. Sometimes they reflect back in your face and all you're looking at is your eyeball. And finally, they go. There's a lot to cover in however long I took. And I've told you pretty much all I know about nighttime observing with filters, probably more than I actually know. And we cannot go into everything that you might want to know about looking through rose-colored glasses and other astronomical filters. But this collection of images gives you some idea of what is happening. These are photographic, and you would not expect this object nearly as well in a visual telescope. But just remember, you get a different view depending on what you're looking through, what kind of filter. By choosing what color light you want to let into your telescope, by using the rose and other colored glasses, you will change what you actually see. Thank you.